Okay, welcome back. Last time we were talking about, instead of regular linear distance, we were talking about angular distance or displacement, or the angle something rotates through. And what we found was that there's a relationship between linear and angular variables. Namely, if we're talking about distance or displacement, the linear distance, s, is equal to the radius of whatever the circle is that we're rotating about, multiplied by the angle that the object, whatever's rotating, is rotating through in radians. We can also call this, and I forgot about this last time, but I've been looking at some other stuff and other people are calling this, we can call this the angular displacement, okay? Theta can be known as the angular displacement. All right, so I'm just going to write that off to the side here. Angular displacement. Basically, just the angle that something rotates through in radians. Now, angular speed. Okay, if we have an angular displacement, if we have how far something, the angle that something rotates through, we could also talk about, well, how fast does that rotate? Recall back when we're talking about linear speed, the equation for linear speed would be, well, speed equals the change in distance over a change in time. How far you traveled divided by how much time it took you to do that. Well, for angular speed, there is also an equation, and we're going to introduce a new variable. But before we introduce that new variable, let's talk about what the equation would be. One of the things you'll see is that when we're coming up with some seemingly new equations, they're just rehashes of the old equations, okay? If linear speed was v equals delta d over delta d, linear speed equals change in distance over change in time. Now that we're not talking about linear distance or displacement, now that we're talking about angular displacement, that d is no longer a d. Instead, it is a theta. The change in angle, in other words, the angle that was rotated through, divided by, well, time's still going to be the same. There's no such thing as angular time, okay? See how similar these are? D is a linear distance measured in, or linear displacement, I'll say, measured in meters. Theta is an angular displacement, the angle that gets rotated through, measured in radians, okay? Now the symbol for angular speed is not just v, it is this kind of curly W looking thing. However, it's not a W, okay? This is the Greek letter omega. I seem, for some reason, to have my classes never refer to this as omega. They'll call it W, in which case I'll yell at you. However, the one thing I won't yell at you for is, and this is a little silly, and no one else will ever say this in your life, but I think, you know, sometimes it helps people remember. Sometimes I end up referring to this as wumbo, okay? This is not a W. It is the angular speed. The technical name for it is omega, and you should know that technical name as omega and refer to that, but for whatever reason, my classes always end up calling it wumbo. So there it is. Now, okay, so there's the equation for defining the angular speed. And notice it's very similar. It's the same format as the linear speed equation. We just have some different variables, okay, different variable names. Now, the relationship between linear and angular speed. How is v related to omega? Relationship between v and omega. Okay, so let's see how we could do this. If we're talking about something moving around, actually, well, here's what I'll show you. If we were to take this equation, okay, s equals r theta, all right, linear distance or displacement equals radius times angular distance or displacement. Let's take that. And let's divide both sides by t. Now wait a sec. I know s is not the variable we usually use for distance, but this is now distance divided by time. And you all know what distance divided by time is. That would be v. This is now theta, angular displacement or distance, divided by time, or in other words, the angle rotated through in radians. We just saw what that was. Theta divided by t is simply omega. So the relationship between these two is v equals r multiplied by omega. Okay? So not only can we go from a linear distance or displacement to an angular distance or displacement, we can also go from a linear speed to an angular speed simply by multiplying the angular speed by r. If you had the linear speed already and you wanted to get the angular speed, you simply take the linear speed of something rotating around, divide it by r, and you get omega. Now, I do want to throw one other thing in here. For situations where we have constant rotation. Now, we did this back in circular motion. If you want to know the linear speed of something rotating in circular motion, you would say it's, well, equal to this. V equals 2 pi r times t. 2 pi r being the circumference, t being, and I'm going to capitalize this actually, t being the period, the time it takes for one rotation to happen. Now, I could change this very simply by switching the places of the t and the v. The period is equal to 2 pi r divided by v. That's also a true equation. The period is equal to 2 pi r divided by v. All I did was, well, essentially, I cross-multiplied v and t. I divided the v over to the bottom here. Okay? Now, we know from over here that v equals r times omega. So I could also say t equals 2 pi r divided by, well, let's see, r times omega. Look at that. Those r's are going to cancel out, and I'm left with a somewhat useful equation. I believe it's on the reference tables, which is why I'm showing you this. 2 pi over omega, the angular speed, is equal to the period. Okay? That's another way of finding the period if you're given omega. Doesn't come up a ton, but since I believe it is on the reference tables, my apologies if it's not, but so I did want to show you that. Okay? We've talked about angular speed. Okay? That's just the rate at which something rotates through a certain angle. Okay? How many radians per second would be the unit? How often or how quickly does it rotate? If we can talk about angular speed, then we can certainly talk about angular acceleration. Once again, let's talk about linear acceleration first. Linear acceleration, you should remember this equation. Linear acceleration is a equals the change in velocity divided by time period. Okay? I bet you can guess what the angular acceleration equation is going to be. Again, I'm going to hide the variable from you for a second. If the linear acceleration equation is delta v over delta t, change in linear velocity over time, well, angular acceleration should be the change in angular velocity. And angular velocity, angular speed, those are the same variable. So we're going to have delta omega over delta t. And the symbol for this ends up being, it's actually the Greek letter alpha. Okay, that is the proper name for this. I am not going to, or I will, you should know that this is alpha and say alpha again for whatever reason. Last year's class ended up calling this, what they call this, I think goldfish or Jesus fish or something like that. Anyways, this is the symbol for angular rotation and the technical term for it is alpha. Okay? Now, as far as angular acceleration goes, this one can get a little tricky. Okay? When we're talking about something that is rotating from circular motion, you know that there is some acceleration, that there is an acceleration called the centripetal acceleration directed towards the center of the circle, the center of rotation. So this angular acceleration can be directed toward the center of rotation and or in the direction of motion. Because if something is rotating, then obviously it has some acceleration towards the center of the rotation, the center of the circle. However, it can also be speeding up as it rotates. When we did circular motion, we didn't talk that much about objects that sped up, that moved faster and faster as they went around a circle. So we can have what's called tangential acceleration. We can also have centripetal acceleration. Centripetal acceleration is acceleration directed towards the center of the circle. Tangential acceleration is exactly what it sounds like. Acceleration directed tangent to the direction of motion right now. So I'm going to give you equations for both of these. Okay? The tangential acceleration equation and how that's related to the angular acceleration is, well, it's the angular acceleration multiplied by r. Again, if I were to take this equation and divide both sides by t, I would come up with this equation, okay? The acceleration, the linear tangential acceleration is equal to the angular acceleration multiplied by r, okay? That's the equation for how fast this thing is accelerating, how much it's speeding up, essentially, okay? As it gets faster and faster. AT is linear tangential acceleration equals the angular acceleration times r. If you want, instead, the acceleration you're a little more familiar with, AC, okay? AC is equal to, well, let's see. Let's just call this AR, the direction towards the center of the circle, not tangential. And we know AC is equal to v squared over r. V, the linear speed or velocity, is equal to r times omega. So v squared should be equal to r squared times omega squared over r, which leads us to, one set of the r's is going to cancel out, omega squared r equals AC. So if you want to write your centripetal acceleration, your acceleration towards the center of the circle in terms of angular variables, there you go. It's omega squared times r, okay? The derivation of these equations is not really the important part. I did want to show it to you. What's important is that you realize that these symbols are not tricky. They're not hard to use. You need to know essentially 3 new symbols right now. You need to know that theta is angular displacement, or if you want to think of it, the angle that something rotates through in radians. You need to know, and it's very similar to x or d, the linear displacement. Omega is angular speed or velocity, very similar to v, linear speed or velocity. And alpha is the angular acceleration, very similar, but with a couple differences to the linear acceleration. You just have to specify which acceleration you're talking about. My point in trying to do this is to show you that so far the definition of angular speed is very similar to the definition for linear speed, but with angular variables, with rotational variables. Same for angular acceleration. Similar to the definition, just has different variables. Angular kinematics equations are exactly the same as your linear equations, but with their angular variables. So we have 3 regular linear kinematics equations. The first is V equals V naught plus AT, VAVOAD as some of you like to call it, or the fiat equation. All we do is we replace the linear variables with angular variables. So instead of V, we're going to have omega, instead of V naught, omega naught, plus, instead of A, alpha, and T will remain the same. So we have omega equals omega naught plus alpha times T. The angular velocity equals the initial angular velocity plus the angular acceleration multiplied by time. If you understood how the linear equation version of this worked, congratulations, you now understand how this one works. You just need to get into your head that these are the variables for angular speed and velocity and acceleration. The second one, I'm going to write down theta equals theta naught plus omega naught t plus 1/2 alpha t squared. Very similar to x equals x naught plus v naught t plus 1/2 at squared. It's the exact same thing, just with different variables, with angular variables. So when we're dealing with angular motion, these are the variables you would use. And in the next video, you'll see that. And the third, omega squared equals omega naught squared plus 2 alpha, in parentheses, theta minus theta naught. The equations are exactly the same, okay? Every year I hear, I don't get these equations, they're just weird, they're uncomfortable. You need to get comfortable with them, okay? You need to realize that these variables are exactly the same, but instead of talking about something that goes in a straight line, we're now talking about something that is rotating through some angle, rotating in a circle through some angle, okay? Once you get that, these are very, very simple equations, okay? You've been using them for the better part of 2 years. In the next video, we'll actually use them. So I'll be right back.